Hello everybody, welcome back to G4 Labs IB Physics, and today we're going to be talking about force and Newton's laws. More about 2.2 essentially. Okay, so Newton's third law, I'm sure you've heard of it before, says that every action has an equal and opposite reaction, right? As you sit in a chair, the chair your weight applies a force on the chair, right? The chair applies the same force back in order to keep you from sinking through it. Newton's third law tells us that forces come in pairs that act against each other. They don't cancel out in the sense that they act on the same object. Rather, one object has the action force and the other has the reaction force. And that makes the forces cancel out in the system because the action and reaction force are equal in magnitude. So there are a bunch of different problems that can require you to utilize Newton's third law, right? And here's one example. Consider two blocks, one weighing 5 kilograms and the other weighing 10 kilograms, that are being pushed from the rear block. So it's two blocks in a row and you're pushing from the back, right? So both blocks are being accelerated at 3 meters per second squared because they function as one system, right? Assume the larger one, so the 10 kilogram one, is the one getting pushed, the one in the rear. What force does the smaller block, which is the one in the front, apply on the larger block, which is the one in the back? Okay, let's see. So here's what our solution looks like, right? Here's what the free body diagram looks like for the larger block, right? So you have F, which is the force that you apply, right? And it is indeed the force required to move 15 kilograms, which is, remember, the sum of the masses of both blocks, because in this case, they're one system. Yeah, it's the force required to move the 15 kilograms of blocks at an acceleration of 3 meters per second squared, right? And if you do your double checking with Newton's third law, it does indeed check out because 15 times 3 is 45, which is the force that you're applying. So then let's ask the question, right? Why doesn't the larger block acceleration become 4.5 meters per second squared? I mean, what's stopping it? The thing that is stopping it is because when you push on the larger block, it is forced to contact the smaller block in order to push the smaller block, right? You're not pushing the smaller block, you're just pushing the larger one. Due to Newton's third law, the smaller block is required to apply a reactive force equivalent to which the larger block is applying on it, right? That's what we read about in Newton's third law. And the two blocks function as one system, right? So when you start pushing the smaller block with the larger block, we can calculate the force the smaller block applies on the larger block in order to accelerate at 3 meters per second squared as well. And thanks to Newton's third law, we know that it is equivalent to the net force on the small block, and therefore it would be 5 times 3, which is 15 newtons. Okay, let's move on. So now we're going to talk about buoyancy, right? So have you guys ever wondered why some things float and other things sink in water? The reason for this is because all liquids apply something called a buoyancy force on the object submerged or partially submerged within them. For a floating object, the buoyancy force is able to balance with the weight of the object, and for an object that is sinking, it is unable to do so. In other words, the weight or whatever is pushing the object down is greater than the buoyant force. Okay, so here's our equation for buoyancy, right? The P thingy, or rho, is density. V is volume of the fluid displaced, not volume of the object that is in the water, or not water, liquid, right? And then G is just G, yeah. So this is also known as Archimedes' principle, and it essentially tells us that the buoyant force is equivalent to the weight of the volume of water displaced by any object, or well, not just water, but any fluid. And this can tell us a lot of things, like super dense objects will naturally sink. And by the way, the density of water is about 1,000 kilograms per cubic meter, so that's what we're going to use in our calculations. In reality, I think it's a bit less than that, but for simplicity, that's what we'll use. Okay, so we got our second problem, right? Some cargo is placed on a barge that is 10 by 6 meters in dimension. The cargo causes the barge to sink 4 centimeters further into the water. What is the weight of the cargo, assuming the barge and the cargo are still floating, I hope, and the barge is floating originally? Okay, so here's what our free body diagram looks like for the cargo, right? So we have the weight of the cargo, which is Fg, and then naturally the barge, because the cargo isn't sinking through the barge applies normal force back, right? And so if you think about it, there isn't actually any buoyancy force acting on the cargo because it's sitting on the barge, not floating on the water. Okay, so here's our free body diagram for the barge after the cargo is set, right? So we have the force buoyancy due to the barge's buoyancy force, right? like when the barge is just on the water by itself, there's already a buoyant force being applied on it, right? So that's where FB sub BG comes from. And then FGB is just the weight of the barge, right? And then we have the we have the weight of we have the buoyancy force that is added due to the cargo, right? Because when you add the cargo, the barge sinks, right? And therefore that displaces more fluid and adds force to it, right? Okay, and then we just have the force normal that the cargo applies on the barge, and that's kind of what cancels out with the buoyancy force of the cargo, right? So yeah, the barge is where the changes in the force actually happen, and the barge experiences all the buoyancy force. Okay. Yeah, so the barge does indeed apply a large amount of normal force on the box, right? But this is only to keep the box from falling through the barge. In order for the barge to stay afloat, more buoyancy force needs to be applied, right? And that's what we just talked about, right? The F sub BC is the buoyancy force that gets added because the barge sinks further down into the water. Yeah. Okay, so using Archimedes' principle, we can see that the volume of water displaced is 10 times 6 times 0.04 or 2.4 meters cubed, and you can verify that yourself, right? So, and then since the barge and cargo are still floating, that means the extra buoyant force balanced out with the normal force the cargo applies on the barge, right? And that's equivalent to the cargo's weight, since the cargo is on top of the barge. Therefore, we can just apply the formula, since we know the rest of the information we need to do so, right? So the buoyant force is equal to the weight, right? And the weight is 1,000 times 9.81 times 2.4. So we get approximately 2,354. Okay, sorry, I cannot talk. 23,544 newtons as the weight of our cargo. And we are done here. Okay, so now we're going to move on to viscosity, right? Viscosity is, by definition, a fluid's resistance to flowing. One way to interpret this is kind of like how thick the fluid is. And for example, like a real life example is that honey. Honey is very thick and it doesn't flow much, whereas water, on the other hand, is, you could consider it thin, I guess, and it flows very easily. Like you can pour it into a cup very easily. In this case, you can think of honey as a very viscous liquid, whereas water isn't as viscous as honey. Right? And due to the nature of matter, faster molecular motion makes it easier to flow, right? Temperature decreases a fluid's viscosity. And then you already saw it in the last slide, but here we'll talk about it a bit more. This right here is Stokes' law. So for a sphere in a liquid, the viscous drag force can be quantified by F is equal to 6 pi, and then that weird N symbol is pronounced eta, so 6 pi eta RV. So here, R is the radius of the sphere that we're in question, right? V is the velocity of the sphere in the liquid, and eta is the coefficient of viscosity. So yeah, each liquid has its own coefficient of viscosity. Okay, we got a third problem now. So a ball of radius 5 times 10 to the negative 4th meters, which is pretty small, fell into a pond of a certain liquid. The liquid in question has a viscosity coefficient of 1.0. Assuming the ball weighs 2.0 times 10 to the negative 6 kilograms, well, that's pretty light. What velocity does the ball finally achieve before it stops accelerating downwards? And for the purposes of this question and practicing Stokes' law, we're going to assume buoyancy is irrelevant for now. Okay, here's what the free body diagram looks like. It's pretty simple, right? So we have Fd, which is the drag force due to viscosity, right? And then we have Fg, which is the weight of the ball. So at some point, the force due to the drag will be equivalent to the force from gravity, as gravity accelerates the ball downwards and the drag force keeps increasing. At that point, since the ball will be in equilibrium, it's no longer going to be needed to accelerate, and it will no longer accelerate, and therefore we are looking for the velocity where the drag force is going to be equivalent to the weight of the ball, or the force applied by gravity. Okay, so then we just set up the following equation by applying Stokes' law, which, remember, is 6 pi eta RV, right? So we have 2 times 10 to the negative 6 times 9.81. Remember, that is the mass of the ball, right? It was 2 times 10 to the negative 6 kilograms, right? And because the weight has to be equal to the drag force, we make it equal to 6 pi times 1, coefficient of viscosity, times 5 times 10 to the negative fourth, which is the radius of the ball, and then v, right? And we're trying to solve for v. So then we rearrange the equation to isolate v, and we get this expression right here on the right. And finally, when you simplify that, you will get that the velocity is going to be 2.08 times 10 to the negative 3 meters per second. At that point, it will stop accelerating downwards. Okay, so remember the previous question, the one we just did, right? The ball falling through the pond of a certain liquid. Now, what happens if we account for the buoyant force? And we're going to assume that the liquid has a density of 3,800 kilograms per meters cubed. Okay, so here's what the free body diagram looks like now. So it's pretty much the same, except now we just add the buoyancy force in the same direction as the drag force. They're both going to be opposing the weight of the ball, right? Yeah, okay. And both of these combined, so the ball is going to stop accelerating when both of these combined are equal to the mass of the ball, or the weight of the ball. Okay, so now we need to actually calculate the volume of the sphere. We know that the volume of a sphere is 4/3 pi r cubed, right? So 4/3 times 5 times 10 to the negative fourth cubed pi. That's going to give us 5.24 times 10 to the negative 10th meters cubed. So a very small ball. And applying that, we get the same equation as before, but now we need to account for the buoyancy force, right? Which, if you guys remember, was rho GV, right? So rho, in this case, we remember that the density is 3,800 kilograms per meter cubed, right? G is just 9.81, and then we have to multiply by the volume of the sphere, which is just 5.24 times 10 to the negative 10 meters cubed, right? Okay, so we're trying to solve for v, so we need to try our best to isolate v, right? So then what we do is we evaluate the buoyancy force on the right, which is 3,800 times 9.81 times the volume of the sphere. We get 1.95 times 10 to the negative fifth, right? So we subtract that from both sides in order to eliminate it from the right side, right? And so we get an equation that looks fairly similar to what our equation looked like last time, right? And so once again, we just isolate v, except this time our numerator is actually just going to have a different value, right? And we find that the velocity is equal to 1.07 times 10 to the negative fifth meters per second. Which, if you think about it, makes sense, right? Because now that there's the buoyancy force also opposing the weight of the ball, right? The ball won't be able to accelerate as much because the drag force has less magnitude it can go to before the two forces become equal to the mass or the weight of the ball. Okay, so let's review. Today we learned about Newton's third law, buoyancy, and viscosity, right? And if we were to sum it up in one sentence, right, we learned that forces come in action and reaction pairs due to Newton's third law. The buoyant force depends on the volume of the water displaced, and the viscosity is kind of like the thickness of a liquid and how resistant it is to flow. And so next video, we're going to learn about momentum, impulse, and collisions. Hooray! All right, thank you guys so much for watching, and please check out our IB Comp Sci and IB Bio videos as well. Bye.